Today, we're digging into one of the most infamous engineering failures in history, the collapse of the Tacoma Narrows Bridge. But this isn't just a story about twisted steel. Oh no. It's the story of how a truly spectacular disaster forced us to completely change the way we design our world.
So here's the central mystery, and it sounds impossible, right? A 42-mile-per-hour wind. I mean, that's breezy, for sure, but it's not a hurricane. We build massive structures to handle way worse than that all the time. So what on earth went so terribly wrong that day in 1940? Well, to figure that out, we have to look at what made this bridge so revolutionary and also so fatally flawed.
All right, let's go back to that day, November 7, 1940. The collapse wasn't just a failure, it was a genuine puzzle. And because it was all captured on film, it became this haunting and very public demonstration of a danger that, at the time, nobody really understood. To put that wind speed in perspective, 42 miles an hour is about 19 meters per second. For a giant steel suspension bridge, this should have been a total non-event, a walk in the park. The fact that it wasn't is what makes this story so fascinating. It wasn't the brute force of the wind that took it down. It was something much more subtle and way more insidious. You know, the craziest part is that everybody knew the bridge was wobbly. From the day it opened, it would rise and fall in the wind in these big, rolling waves. People nicknamed it Galloping Gertie. But here's the thing, at the time, the engineers just saw it as a harmless quirk, a side effect of its super flexible, modern design. They had absolutely no idea they were looking at a symptom of a catastrophic flaw.
So how did a team of brilliant engineers get it so wrong? To understand that, we've got to look at the design itself. The Tacoma Narrows Bridge was supposed to be the future. It was the peak of this new philosophy that was all about elegance and saving money. But that very same pursuit of grace turned out to be its fatal weakness.
Just take a look at these numbers. The bridge had this incredibly long main span, over 850 meters. But the deck, the roadway itself, was only 2.4 meters deep. That is ridiculously thin. It created a span-to-depth ratio that nobody had ever seen before. This whole thing was driven by a concept called deflection theory, which basically argued that bridges could be way more flexible and lightweight, which, saved a ton of money on steel. It was the absolute cutting edge.
And this right here shows you the problem in a nutshell. On the left, you've got your traditional bridges. They use these deep, open steel trusses. Wind could just blow right through them, no big deal. But then you have Galloping Gertie on the right. It used solid sheets of steel, these plate girders, to get that sleek, modern look. The problem was, instead of letting air through, it acted like a big, solid ribbon, trapping airflow. It essentially turned the entire bridge deck into a poorly designed airplane.
So we've got an elegant design that's also an aerodynamic nightmare. Now let's get into the physics of what actually happened on that windy November morning. This is where we find the real culprit.
Now, there's a common misconception that the bridge collapsed because of resonance. Like pushing a kid on a swing at just the right moment to make them go higher. But the real villain here is something far more complex and interesting. Torsional flutter. It's a self-excited instability. The key is that the motion of the bridge itself creates the aerodynamic forces that then feed even more energy back into the motion. Think of it as a vicious cycle, a positive feedback loop from hell. It all starts with a little twist from the wind. That twist changes how the air flows over the deck, creating lift. But here's the kicker. That lift then pushes the deck, amplifying the twist even more. This feeds more and more energy back into the system, and the cycle just keeps repeating, growing bigger and bigger, totally out of control. It's just like microphone feedback, that horrible screeching sound you get when a mic is too close to a speaker. A small input gets amplified over and over until the whole system overloads. And the result was absolutely terrifying to watch. The twisting, the torsional oscillations, they just kept growing until the deck was tilting at more than 40 degrees from horizontal. At that point, the steel and concrete just couldn't take it anymore. The constant bending back and forth was too much, and the whole structure started to tear itself apart. The collapse of Galloping Gertie was a massive shock to the engineering community. One single failure, captured for the whole world to see on film, forced a complete and total revolution in how we design and test pretty much any major structure.
Seriously, you can literally draw a line in engineering history right at the year 1940. Before then, design was mostly based on what had worked in the past. If a bridge stood up, you just built the next one a little bit bigger. Aerodynamics was, well, it was basically an afterthought. But after the collapse, everything changed. Design had to be informed by physics. Aerodynamics suddenly became a central, absolutely non-negotiable part of the process.
And this wasn't just some change in philosophy.
It led to real-world practices that are completely standard now. Things we take for granted, like mandatory wind tunnel testing for big projects, or building complex models to test them. All of that came about because of this one disaster. We didn't just start building stronger, we started building smarter.
So here's the really crucial point. The big lesson wasn't just make bridges stiffer. It was make bridges more aerodynamic. Instead of just fighting the wind with brute force and tons of steel, engineers learned how to shape structures to work with the laws of physics, to actually control the airflow and make sure the whole thing was stable. It was a huge shift from resistance to management.
So the legacy of Galloping Gertie isn't just about bridges, not by a long shot. It's a powerful, timeless lesson for any field where we're pushing the boundaries of technology and innovation.
This table really sums it all up perfectly. Before 1940, the goal was simple: resist static loads. The key metric was just material strength. And safety? Well, it was mostly just assumed based on past successes. But after 1940, the whole game changed. The goal became managing the dynamic behavior of the entire system. And safety wasn't assumed. It had to be proven and validated through a deep physical understanding of the forces at play.
In this quote, it just gets right to the heart of it. The engineers who built the Tacoma Narrows Bridge weren't bad at their jobs. They were pioneers. They were using the best knowledge available to them at the time, operating right at the frontier. The failure happened because their innovation, their ambition, outpaced their scientific understanding. And that's a profound warning about the real risks you take when you push the boundaries.
And that leads us to the big final question for all of us. The lesson of Galloping Gertie is that when you optimize for just one thing, like cost or elegance or efficiency, you can have catastrophic, unforeseen consequences somewhere else. So as our own modern systems, from artificial intelligence to global finance, get more and more complex, we have to ask ourselves, what critical physics have we maybe overlooked? What Galloping Gertie are we building right now?